Life is just busy. It's just, I didn't get to it. I promise I was not slacking off too much. Anyways, but I don't give up on me. I get to it. All right, so today I wanted to continue, well, finish the batch excursion. And already on Thursday, that is like in 2 days, we should talk about some online learning. But today it's still the dark day, so we're going to talk about batch learning and lower bounds negative results. Which I think are pretty important to get our like compass straight and like pointing us in the right directions of where not to go to. So this result, we started to talk about in the last lecture. And it starts, it's a result by Andrea. It's a quite recent paper. It starts with the definition of this pie design. So in this idea of the pie design, you have a sequence of policies, a sequence of number of steps that you want to kind of unroll those policies. And the policies are deterministic, and you have a bunch of initial states as well, as many as the number of policies. And for every sample size n, you have such a design. And the property that n satisfies is this, that the number of steps that you're making with the policies is never more than n. It can be n. Normally, it would be n. And the idea is to be really, really permissive with these designs. So if you have a pie design, the information that you get by running this pie design for a given sample size on some MDP is going to be all those state action pairs that you can obtain by starting one of these policies. Let's say that the first one, you started from the corresponding initial state, and you follow it for the corresponding number of steps, and whatever state action pairs you encounter along the way during these number of steps, you collect all of that. And this is really permissive because it's like, it's the set of all the reachable states in that many steps. It's like whatever small probability you reach a state, you get, like, you're gonna say that, well, I have access to that state action pair. So it's super permissive. And maybe we would expect then that with such a permissive design, you can cover a lot. And in the model of Andrea, the way you're gaining information about the MDP is also very permissive. There is no noise on the rewards. You get to see the rewards exactly at a set Z that you encounter this way. Sorry, at the state action pair Z, and you're gonna see the next state distributions as well at the same set of state action pairs. So it's like no noise. It's clean observations. So you get all these clean observations, and it's like for all reachable state action pairs. And now you wonder about it. Okay, with this, we should be able to do a lot, especially if we're choosing good pie designs. So then the result's going to be a little bit of surprise, because it turns out that still nothing much can be done, even if you have this setting. So this is where I failed the last time. Let's copy. Paste. Good. Right. Yeah, I was just trying this copy paste before and it didn't work. This time it works. And so the first theorem in this paper of Andrea, we're talking about off-policy evaluation. There is a fixed target policy that the algorithm is going to get as an input. Well, it's going to be like some target policy, and the algorithm is going to get some features, and then it can use a row design, sorry, a pi design, just ideated by a row, and it can use whatever row, whatever pi design, sorry, it wants to have. It doesn't matter, because the result says that if you have an algorithm which is sound, by soundness here we mean it's policy evaluation. So we're going to mean that the algorithm can estimate the value of this policy up to some fixed accuracy, like 1/2 accuracy, constant accuracy. And the probability that the algorithm is making a mistake is not 1, so it's less than 1. It's some number. Doesn't matter, like 1/2, at most 1/2. So we're very permissive there as well. We don't demand that the algorithm always returns a constantly accurate estimate of the value of the policy. There's going to be an initial state as well. But we just demand that happens with some positive probability. And so if you choose an algorithm, like whatever algorithm that has this guarantee, then the sample size, no matter how the pi design is chosen, at which this algorithm will be able to deliver on this promise, is going to be exponential in the horizon. So here, age is, this is discounted problems. So h is 1/1 minus gamma. So in this pi design, no matter how it's chosen, you have to get up to a sample size of at least h to the power of d, well, h/2 to the power of d times the square root d, to be able to guarantee that the algorithm succeeds, regardless of the algorithm. And the target policy, so here the condition is that the target policy has an action value function that can be represented with the features. And the feature map is available to the algorithm globally, right? So it can pre-process it, it can do whatever with it. Okay, just to recap again. So the problem is that the algorithm is going to be fed with the feature map. It's going to be fed with this target policy, and an initial state, and it needs to estimate the value of this target policy at the initial state. And the promise the algorithm gets is that the target's policy action value function is linear, exactly linear. So it only needs to estimate d parameters, these dimensional to the feature map. And there is nothing tricky with the feature map. It's just the usual feature map with bounded features. And no algorithm can do this without asking for exponentially many of these very, very strong type of observations. Okay, so that's the result. How does this work? So there will be three results of this type, and the proofs are pretty similar to each other. And the idea is going to be always that if you have a d-dimensional unit ball, so B is going to be my d-dimensional unit ball, Here's the origin. Then if you take a unit vector W, then you can take these caps. These are called hyperspherical caps because this is a hypersphere. So the shaded area is, so it has one parameter. So the length of the radius here, so the radius is 1, and this distance here is gamma. That will be the same gamma as our discount factor. So gamma gets to large, the shaded area, you can feel that it becomes really, really small as gamma gets close to 1. So this shaded area, to be precise, is all those points in the ball where the inner product between the ball and the chosen direction W is at least gamma, right? So we in fact have seen something similar to this, right? So when we were using the Johnson-Lindenstrauss theorem, or lemma, then we were talking about how many vectors can you fit on the sphere such that the inner product between distinct vectors is uniformly small. So here we're talking kind of like the opposite. We're just talking about like this cap, and but it's gonna be the same because we're gonna say at the end that, well, if you choose some gamma, then you can look at how many of these caps you can fit on the hypersphere, and you will find that the number of caps that you can fit on the hypersphere in such a way that none of these caps are overlapping. So that's like, you know, the inner products between these guys are gonna be necessarily not large, right? So the number of these caps which are disjoint is going to be lower bounded by square root d times h gamma over 2 to the power of d, where h gamma is just this 1 over 1 minus gamma. And you can calculate this by just using volume calculations. So this is good old-fashioned analysis, volume calculations. All right, so this is the tool that we're going to use in all the proofs. And it's like you can feel that it's very similar to the Johnson-Lindenstrauss idea and construction. Okay, how does the proof of theorem 1 work? How do we use this result? So let's call this a lemma. So we need to choose, so we are given some algorithm A and some pi design rho. So what is that MDP and feature map which is going to force this algorithm to use a large sample size? So the MDP needs to have states, actions, transitions, rewards. I'm going to choose a family, and the family is going to be indexed by some unit vector. So this is this lives on the sphere, the unit sphere, and it's going to be parameterized by just a sign. And the transition is not going to depend on that, but the reward is going to depend on this W and the sigma. And the state space action space is all the same. The states and the actions, they're gonna be just the unit ball. The initial state is going to be 0. The dynamics is going to be deterministic, and then when we have this deterministic dynamics, I just write this like, what's the next state function? So given a state and action, the next state is going to be A. So that's just linear dynamics. It's super simple. And the reward, finally, is going to be where this cap is going to play a role. So the reward is going to be sigma times 1 minus gamma and the inner product between A and W if this inner product is large. That is, if we are within a cap, then we get this reward, which is proportional to the inner product, and the sign. Either this is a good reward or a bad reward, depending on whether sigma is positive or negative. If sigma is positive, then you want to be aligned with W. If sigma is negative, then you want to align with negative W, and 0 otherwise. So you can imagine this picture where you have this ball. You choose a W. So that's your W. That is your gamma. And in this region, the reward is increasing with the inner product. So if I project it, and this, okay, in this region as well, except that here it's negative. So this is very cold, and here it's positive. So the good stuff is on the right on this figure, the bad stuff is on the left. And another picture would be that where the inner product can go between -1 and +1. So this is the inner product between A and W. And then the reward is going to be 0 up to this point. And otherwise, you take, well, okay, for the sigma equals 1, sigma equals +1, you go up to 1 minus gamma. And here there is the negative of 1 minus gamma. So that's a little bit smaller than 1. And so if you connect this, then this would be the reward function, except that at gamma, you step in and you threshold it with 0. So it's like, all right, so if we greater than equal, then it starts there. This doesn't belong. This is how it looks like. So this is piecewise linear reward function. Okay, that's our reward. This is our reward for, sorry, this is yes, okay. This reward. +1 and ANS. Right. This is the reward. And okay, so what's the target policy? So we need to feed the algorithm with a target policy as well. The target policy is not, yeah, like it's going to depend on W. And it's going to be equal to it doesn't depend on sigma, but it depends on W. And it's going to be this policy. You take the state, you take the inner product with a W, divide by gamma, multiply with gamma. If this inner product is less than gamma, and you return the state otherwise. So how does this work? So if you imagine that this is your W, this is your state space, and you're at some state here, okay? And here's your gamma. What's the inner product between W and the state? Well, it's basically you have to take the state, project it down on W, you get this distance. This is the inner product between S and W. And you look at this and you say, well, okay, this is on the left side of this line. So it's this inner product is, so it's actually, there's a negative sign as well. So it could be here. And the similar thing would be happening to this state. So it's like between these two lines. And if it's between these two lines, then you make a step. Well, you choose the action, which is let's calculate how far this is relative to thinking about this whole distance of being 1. So that's going to amplify this by a factor of 1 over gamma. And let's make a step along W, because the dynamics, recall, is linear. And if you apply an action, then the next state is just the action that you applied. So when the policy says that let's choose this action, this is going to be the next state. So altogether, if you interconnect the policy with the dynamics, then what happens is that, well, there is this projection. We look at whether we are in between the lines. Yes, we are in between the lines. Then there is this magnification by the factor of 1 over 1 minus 1 over gamma. And we make a step along W. And so we lose the orthogonal component to W right in the first step. And after this, what happens that the process repeats if you follow this policy, right? And it just like goes there. And then it stops there because when you are there, then the policy says, oh, like, let's just stop in place. And then you start to collect the reward. And the reward is this normalized inner product. And so from that step on, the total accumulated reward is going to be sigma times A transpose W. So one can feel that somehow, yes, maybe this is going to be good if we choose for the feature map, we just choose the action component of the feature map. And indeed, first we need to verify whether it really does hold that the action value function of this policy is linear in the features. So is it true or not that somehow this is equal to to this with some parameter. To get a conjecture of what that parameter could be, if you start the whole process in this cap, then we know that the total reward collected would be sigma A transpose W. So we might conjecture that the answer to here of what this theta could be, that theta should be maybe, if anything works, then sigma times W is the value that's going to work, because that's what's going to work in the cap. So let's make this a claim. So how do we prove a statement like this? Give me some ideas. How would you prove it? So you want to prove that this theta parameter is really such that this action value function of this target policy in this MVP satisfies this. Simple ideas. I will not ask you to do it. I will do it. Do you want an extra homework? No. Yeah, we could check directly. So Wesley suggests. So that would mean that directly calculate the action value function. For simple cases like this, there's a chance that you can do that. So check directly. What's the other option? Which is sometimes a little bit faster. Yeah, Fengi says, good. Bayerman equation. Right. So how can we use the Bayerman equation? So I can write the Bayerman equation. So the Bayerman equation, so let's abbreviate this policy just to pi, okay? Because it's too much to write. So the Bayerman equation says what? It says that, well, this should hold, right? Take the immediate reward at gamma and make a step. With the dynamics. Oh, and then plug in into the Q function where you take the action that results from taking the step. Ooh, okay. It was a lot of writing. So we can try to verify whether the linear expression that we got satisfies this equation. Why is that sufficient? To know that Q pi is going to be linear. How many solutions can we have for this equation? If I view this as an equation in, you know, come on, F. Like, oh, no, not F. Okay, call it Q. How many Q functions satisfy this? It has a unique solution. Good, right? So it's sufficient to verify whether phi transpose sigma phi SA, this thing satisfies it, right? So this is just sigma A transpose W. So map S and A to sigma A transpose W. Does it satisfy or not the Bellman equation? If it satisfies, we're done. So the dynamics is super simple. So lucky for us. So this is just A, and this is also just A, right? So the Bellman equation rewrites that we need to see whether this is satisfied. And then here, oh my gosh. So the state doesn't matter in my linear expression, only the action matters. And then here I have to take whatever action the policy takes. And that's at A. So we need to verify this. And there are two cases because, well, the reward and the policy both are defined in a piecewise manner, depending on whether you're in a cap or you're not in a cap. So case 1, A transpose W is at least as large as gamma. Then, okay, let's just write the right-hand side. We see what the left-hand side is. So the right-hand side is going to be, what's the reward? It's sigma 1 minus gamma A transpose W. And the other guy, the policy, what does the policy do when we are in a cap? When we are in a cap, the policy just returns S. So it just returns whatever it is fed with. That's A in this case. And there we go. This is indeed equals sigma and the inner product between A and W. So that's good. Case 1 verified. How about case 2? When this holds, then the right-hand side. So what happens to the reward? The reward is 0. And what does the policy do? Well, the policy is this, let's take the state in the product with W divided by gamma times W. All right, so that's gamma times W transpose W. All right, so that's good because gamma cancels. This is 1 because we had a unit vector. So this is also sigma times A transpose W. Right, so case 2 is also verified. There are no further cases. Case closed. We see that the claim is true. So it's true that the action value function of this target policy is linear in the features. All right. So now back to the proof. Why did we do all of these things? So recall that the algorithm, so there is this algorithm that uses this pi design with some sample size. And we have this dynamics, which is a deterministic dynamics. And so in the pi design, the algorithm is, asking for, what are the reachable set of state action pairs from such and such initial states with such and such policies. So this is the same as just asking for n state action pairs, because the dynamics is deterministic. You can't overgenerate by saying, like my policies would be stochastic, or like dynamics is stochastic. There is nothing like that. So with a sample size of n, rho is going to induce n state action pairs okay. And the algorithm is going to get all this information about the MDP at these state action pairs. So what is the information that it gets? Well, it gets the dynamics, but it knew the dynamics beforehand, because the dynamics is not dependent on the W or sigma. Okay, so that's you can safely ignore. The algorithm could have optimized for these dynamics if they wanted to. They can. That's all fine by us. It also gets to see the reward. And now we're going to choose the reward in an adversarial fashion. So let's say that the sample size is not large. So let's say that the sample size is smaller than this critical threshold, n gamma delta. So let's say n is smaller than n gamma, d, right? Then we can choose a W. We can imagine where we don't care about the state so much, because the rewards don't depend on the state, right? Like the rewards only depend on the actions. So let's not worry about where the states are. But you can draw where the actions are, and the actions would be like A1 is here, while A2 can be here, A3 is there, and so on and so forth. AN is there. And since there are not too many of these, you can always throw this spherical caps that correspond to the actions that are chosen by the algorithm. And the way this threshold was selected is that if you choose any number smaller than this threshold, you can always squeeze in yet another spherical cap. So then there will be, there is W such that the spherical cap of this W on not on the positive, neither on the positive, neither on the negative side, is going to have an overlap with the spherical caps corresponding to these actions. So if you have too few actions, then there is always space left for one more of this little cap. The figure doesn't give just to this, but like these regions are tiny, right? Like in high dimensions, they're really, really small. So there exists a W such that this, did I introduce something for the spherical cap? Yeah, the C gamma W doesn't intersect with C gamma AI, and the C gamma negative of W doesn't intersect with C gamma AI. And this holds for all I from 1 to n. And so if we take this sigma, if we take this W, then we can choose sigma to be either plus or minus 1. The algorithm will get, well, the algorithm gets information about the reward, but the reward outside of this region is 0. And these actions where the algorithm is getting the information about the reward and the transition, but that doesn't matter, is outside of these regions. So all that the algorithm sees is 0. And here we have two reward functions. In one case, the value of the target policy. So what's the value of the target policy? So it's going to be sigma A transpose W. And so, for example, if you take, you ask the algorithm, okay, what's the value of the target policy at, I don't know, A equals W, then the answer should be sigma. But this is the information that the algorithm is going to lack. So the algorithm never gets to see the sign, which can only be seen here. So the algorithm has, like, it could randomize, and then it has half of chance of getting the sign correct, but not more. So if we demand that the algorithm is correct for more than half the time, up to an accuracy of, I don't know, less than 1, then we see that the sample size necessarily have to be larger than this n gamma d quantity, which was this exponentially large quantity. All right. So that finishes the proof of this result. Okay. So what's the lesson? Well, I guess one lesson is that this linear function approximation is not such a big help when it comes to passively learning. Because yeah, like MDPs are just like have a very rich structure, and the information that you need may be hiding in some corner. And with a passive design, you may never encounter these corners. With an active design, in this case, if you have this target policy and you need to avoid it, it's absolutely no problem. because you can just like ask what the policy is going to do at some points, and you will get W from there, right? So the policy was, where is this policy, right? Like it reveals W. It has W in it all over the place. And once you know W, so for example, you could feed these policy with the unit vectors, I don't know, divided by 2 gamma. Then basically you get W, right? Like you get all the coefficients of W scaled. And you can calculate W, so now you know the direction, and then you can feed the policy with W, and from that you will get sigma, right? You can directly ask for the reward at that state. Like you don't need to feed a policy. I'm like, you know where W is, and then you say, oh, well, what's the reward at W for this action that is W? And then you get sigma times 1 minus gamma. So it's like, you know, sigma, and then you're done. You can avoid any policy whatsoever after that, not only pi. So the information can be obtained in an active manner in this case, in a very simple manner, very simple way, but the passive data collection is kind of like lost because these spaces are big, and you can hide information in some corner. So linear function approximation looks like it should be doing a lot, but it's only doing a lot when you have some sort of active way of interacting with the problem instance. All right, so that's the first result. The second result is, so this was for the case, so first result was for evaluating a fixed target policy. Which is linear. And the next result is for the case where Q star is linearly realizable. And the result, well, we know, like I was thinking, because for Q star linearly realizable, we already had a negative result for planning. So then why would you expect to see anything positive for the harder batch case? The passive case is definitely just harder than the active case. So in the active case, we already had some negative result, but that negative result was in the form of, I don't know, was this form, like, so planning, it was d to the power of, no, sorry, it was 2 to the power of omega and the smaller of d and h. So it was an exponential lower bound of this form. And I didn't do the proof for the discounted setting, but you can get the same for the discounted setting. So here we are in a passive setting, and what we're going to find out is that the sample complexity is going to be larger, because otherwise this would not make any sense, right? So it's going to be even worse. Like if this was not bad enough, it gets worse. It gets as bad as in the previous case. So again, the result is going to say that for every gamma and dimension and every row pi design, so no matter how clever you are about your passive design, for every algorithm that is sound, and we only require Q star estimation for some initial state. There exists a featurized MDP such that, you know, the features, okay, they're gonna be d plus 1 dimensional, but I mean, it's pretty much the same. They are nicely normalized. Q star lies in the span, and okay, so there exists some initial state as well, such that the sample size that this algorithm is going to need, I don't know, with this row design, is going to be exponential of the same form as before, as in the previous result. So here the difference is that if both d and h are small, then this is not so problematic. But here, if d is running away, then like that's already pretty bad. Right. Right. So for the proof, it's a similar construction than before. With slight changes. So B plus is going to be all those vectors in the unit ball whose components are all non-negative. So it's like the positive quadrant section of the unit ball. So that's your B plus. And the state space is going to have 2 special states, S0 and S1, and all these states in the positive quadrant of the unit ball. The action space is going to be like some action T, which is for terminating stuff, and then all the actions in B plus. And the dynamics is going to be funkier in this case. There will be a W, which is going to be on the boundary of the sphere intersected with the positive quadrant. So it's some vector here. And sigma is going to be either 0 or 1 in this case. And the dynamics is going to be stochastic. And maybe it's the best if I draw a figure for it. So the way it looks like is that you're at S naught. That's really special, because from S naught you can choose to terminate. So here you have this action T available to you, and then you go to S1. And if you're at S1, then you stay at S1. You receive a reward of 0 by doing that. So S1 is just like this terminating state, which gives you a reward of 0. When you're transitioning to S1 from S0, you get a reward of 1/2. And so the decision problem is going to be to decide from S0 whether you want to take this immediate terminating action, or you want to jump into this positive quadrant somewhere, and then you're going to do your thing there. And the thing there is going to be similar to what we had before, except that the dynamics is a little bit funkier. So the dynamics is going to depend on W. And if you're at state S, then the next state distribution is going to be either a Dirac, that is just the action that you chose. So either you know, like you're at this state, you choose some action, it's here. So with some probability, and let me call it, I don't know, PWA. So PWA probability, you just go here, that's your A, this is your S, or you jump out. So that happens with 1 minus PWA probability. And if you jump out, then you get to S1. All right, so I don't know why I redrew this figure, but for that, it's better to zoom in. So to finish, either you jump to S1, or you jump to whatever action you chose to that state. It's like switching, like probabilistically switching between these two choices. And the PWA is just the minimum of the inner product between A and W divided by gamma and 1. So that's like this function. It grows until you hit gamma, then you're at 1 already. So you don't grow any more further. So this is this is A transpose W, the x-axis, and this is this probability that you actually gonna jump to the state which is equal to the action that you chose. So that's that. The reward function is going to be kind of the opposite, but here sigma is also going to play a role. So this is sigma times. So if you choose 0, then there is absolutely no reward ever. And otherwise, you choose the maximum of the inner product minus gamma and n0. So the figure that corresponds to that, this is the reward. Yeah, just the reward. and this is A transpose W. So here we go again, gamma and 1. And so, all right, so let's say sigma is equal to 1, because otherwise, what am I drawing? So this is growing linearly, but like you have to shift it back by gamma, so it's actually just growing like this, right? And it's growing up to 1 minus gamma, right? At the linear growth rate. Right. So the optimal policy, what is the optimal policy here? Well, if sigma is equal to 0, then the optimal policy would do what? Oh, okay, there are some important details. Yeah, we at S1, yeah, okay, that's okay. Do I need anything else? Oh yeah, like when you jump from S0 to the MVP, then you get a reward of 0. The dynamics is the same as the dynamics for any other state. So here the state is either S0 or any state in this positive quadrant. Okay. So if you ask, okay, what shall the optimal policy do? Well, if sigma is equal to 0, then there is no way to get any reward whatsoever. And so at state S0, the action to be taken is the terminating action, which gives you a reward of 1/2. And that's the optimal action. The other action, the other actions, all the other actions are going to give you a reward of 0. And this also holds for every other state. Okay, this is, so for every other state and every other action, so S is not S0, and A is any action that's available in that state, you get 0. If sigma is equal to 1, then the optimal policy, okay, if you need to guess, what is the optimal policy doing? There is reward in this little cap here. So you want to go and get it, right? As quickly as possible. How can we get that? Well, we should jump there, right? Like we should just take the action that takes us there. So the optimal policy at S0 should be, and every other state except for S1, because at S1 you don't have, I guess at S1 you can, like, any action like gives you the same 0, so it doesn't matter what you do there. So just take W. And Right. So what does this do? So on this figure, we are here, because the inner product of, so we are here. Inner product between the action we take and W is 1. So with probability 1, we jump to where the reward is, and we collect the reward, which is 1 minus gamma, and then we continue doing that, right? So this means that you get a total reward of 1. So if you take any, of course, if you take the initial state and you take action T, then you still only get 1/2. If you take action 1 and you take any action whatsoever, then you still get a 0. But if you take any other state, okay, I guess no, we have to calculate. And you take some action, then you get the reward of the action plus I don't know, gamma times. Oh, this is right. This is okay. Like a little calculation, right? Because you have to take into account. Oh, I just wanted to write V star. So let me just finish it by writing what V star is. So V star of S is going to be just 1. Not S. V star of S? Yeah, V star of S is going to be 1. Like, no matter where you are, you jump to this very special place where you get the reward of 1 and you live there forever. And the only place where you can't do this is state S1, I guess. All right, and then I guess Q star SA, we can calculate what it is to see whether we can come up with some feature map. Is going to be RAS plus gamma and P, I don't know, WA. And with this much probability, the next state is going to be action A. Right, so this holds if S is not equal to S1. Plus gamma times minus PWA, and then you start you jump to V star at S1, and V star at S1 is just the set value of 0. Right? So what's RAS? RAS is sigma max A transpose W minus gamma 0. What's PWA? Well, it's the minimum of E transpose W over gamma and 1. Right. And times, okay, so in this case, sigma is equal to 1, so I don't have to write the sigma there. And so if we go back to this figure, what we see is that there are these two functions of A transpose W, okay? And we scale with this probability function by gamma, right? So imagine that this is scaled down by a factor of gamma, so it only goes up to gamma, and then you add the two guys to each other. So if this guy goes to gamma, then the slope here goes like traveling a distance of gamma on x-axis, travels the distance of gamma on the y-axis. Its slope is 1. It's the 45-degree line after scaling down. So gamma times PWA is like starts off a 45-degree line, then it flattens out. And then you add to this other guy, which is like 0 up to gamma, and it continues as a 45-degree line. So all together, you get y equals x. So that's the sum of these two functions. So the sum of these two guys is just A transpose W. All right, so that shows that we can choose our feature map in a not too complicated fashion, right? So Q star has very convenient properties for both sigma equals 0 and sigma equals 1. So we can choose, I don't know, so the feature map could be chosen to be so that's it's going to be A0. Like it's going to be D plus 1 dimensional, so we can accommodate this 1/2 here. So we add an extra dimension for the sake of having that. And so this is when the action A is in the positive quadrant, and otherwise, when you have this other action, basically when you have this terminating action, then we just have a 1 there. And for S1, so this is for S not equals to S1. And for when the state is S1, then you just choose the 0 feature vector. Because then what happens is that, well, for the sigma equals 0 case, you can just choose as the parameter vector that gives you Q star, just a big fat 0 everywhere up to the last 1/2. And for sigma equals 1, the theta should be just W and 1/2. All right. So we created a special feature dimension to handle this just one very special action, but otherwise it's just the usual deal. The feature vector gives you basically the action. So with this, it follows that Q star for whatever sigma and W choose, for whatever state and actions you choose, is going to be equal to the inner product of, okay, so let's call this sigma W. The inner product between the feature map and this theta parameter vector. And then the story is kind of similar to the previous one, because if the algorithm chooses some pi design and it has a small sample size, it goes in with the pi design. Now, where can it go? Well, it can only go whatever actions those policies are going to choose and state S1, right? Like the stochasticity and transition dynamics doesn't matter that much. So the pi design doesn't give you more power than choosing n state action pairs, in addition saying that, well, in S1, I want to know everything, but like you already know everything in S1. So pi design has the same power of choosing just n state action pairs. And from those, the only thing that matters is where is this little cap, so that you see whether there is reward there or that there is no reward there. And again, if you have only so many, so this is the positive quadrant. So you might suspect that you have to divide by 2 to the d, because there are 2 to the d of these quadrants. The sample complexity result that we had, I guess, like, I'm kind of missing there. 2 to the d should be there. Or maybe that was that. No, I don't think so. There is an extra 2 to the d less in the sample complexity. But other than that, like, if you have all these actions, then you can always choose a w that avoids all those actions. And as long as the sample size was small enough, and in this case, the algorithm has no better than a random chance of figuring out whether it should go to the cap or it should right away go to S1. And so it can't avoid the initial state, and it doesn't know what to do in the initial state. And clearly, if we allow an active algorithm, then at least for this very restricted problem, the active algorithm is going to have a beautiful chance of figuring all this out. And how? Okay, let me think. Oh yeah, so the algorithm, like, remember that there is no noise here. So we learn the transition. Okay, so in the easy case, when we completely learn the transitions, which we assume we're gonna learn completely the transitions, everything that we encounter, then you immediately learn from these expressions. If you poke the dynamics again at the unit vectors divided by 2 gamma, then you can learn the value of w, because then you're going to be in the linear section of these probabilities. And then from there, you can figure out what the w is. And once you know what the w is, you just jump there and see whether there is reward. So it's the same story as before. All right, I'm going to stop here. There is a third result that I couldn't get to. So that result is for Q pi realizability. So it's the same story, but in this case, for every policy in the MDP, we assume that the action value function of the policy is realizable. And no matter what sound algorithm you choose, unless the sample size is of the same order as before, the algorithms are going to have hard time either figuring out what is a good policy or just avoiding some policy that we choose. And the construction is very, very similar to the previous ones. It just caps in this linear dynamics and like just a really simple construction that we had before. So yeah, and again, in the active case, there is an algorithm that can get everything. So the story is that yes, this passive design is maybe not the brightest idea, and we should let ourselves to interact with these MDPs because we have a really hard time of getting any information whatsoever, even under like for pretty small classes of MDPs which are linearly compressible in like good ways. We have a very hard time of getting any positive results. The only positive result that you're able to get are under these closeness assumptions, when basically the MDP itself, the dynamics and the reward are compressible with a few parameters. And then you just learn the MDP, and then you're in a model-based case, and then we cover that like, oh, if you know the model approximately, then you know approximately what to do, so there is nothing really spectacular there. So that's, in a nutshell, like all the effort that that goes into relaxing the requirement that for the batch case we demand that we kind of just can learn the dynamics, it doesn't work. Doesn't seem to do much, and provably doesn't work. It's not like that. We are too lame and we can't figure out the right algorithms, but just there are no algorithms that would work. It's still too rich, too big a class. And so next time on Thursday, we're gonna move on to hopefully more rosy waters where you can interact with the MDP, but you're a little bit hampered by the fact that you're paying for your mistakes while interacting with the MDP. So unlike in a planning case where there are no mistakes, like you can try whatever, like you pay with your time, with your compute time. That's the only currency that you have. In the online learning case, the real currency is reward, and you care about how much reward you collected. So if you're missing out reward, that's not good. So you really have to balance out information need with like how much reward you collect, and we'll see that that leads to new challenges, but at least it's interactive. So maybe there is some hope that some of these things, some of these techniques that are meant to work for large MDPs can survive. We will see. All right. Let's stop here. I'm gonna stay around if you have any questions, but we can also stop recording.